So in this video, I'm going to focus on inductance, but before we do that, there's a few more questions remaining, so I'm going to get over these ones and then we'll move on. This is just like in the previous video. This question is asking, how could you make the bulb light up? If you want to make the bulb light up, we must induce a current. Inducing a current means I must change the flux. The flux being B, A, cos theta. I must change either the field, I must change the area, I must change the angle. This will work. Now, moving the bar right or left. Moving the bar right or left will change my area. This is my current enclosed area. If I move my bar to the right or even the left, I will change my area. I will have a stronger or a weaker field. Either way, I will induce something. If I move it parallel, so that means like in or out, that means the field is constant. All of the lines are going in. All of the lines will be facing in that same axis. So moving it parallel, that means I will make no change at all. It will be a constant field that's moving through. So that will not help. If I increase the magnitude of the field, yes, if I increase the magnitude of the field, I will induce a flux. I will induce an EMF based on that. So 1 and 3 are good for this question. Down here, we're talking about a generator, and we want to know which of the following statements on this generator is not true. So let's see. The average induced voltage doubles if the frequency doubles. The frequency is how fast it's spinning. The faster it spins, of course, the more there will be. It's related to sine 2 pi ft. The frequency is important for the EMF. You can also guess, because if it's moving faster, you can even think about the BLV formula. Anything that moves faster will induce more. We did this in a little simulation. We took a magnet, we moved it around through a coil. We even went to the lab and tried it with some of our classes. We went in and out slowly. It got me some EMF, but if we moved faster, we got more EMF. So this actually is true. So this is not the answer that I'm looking for. The average induced potential difference doubles if the resistance doubles. Well, if you have a bigger resistance, it's going to block the induced EMF. So doubling the resistance will make it harder for my back current to go. Actually, this is a good answer. This one is not true. It will actually reduce the potential difference, the EMF induced. This will reduce, not double, if I double the resistance, because it's more blocking the back EMF. The average induced potential difference doubles if the field doubles. Yes, it does. If the field doubles, the EMF will double. EMF, if you remember the formula, EMF equals negative flux, change of flux over time. So yes, this is actually a good answer, which is not what I want because it says it. I've already got the answer, but I'm just explaining why every other one will be wrong. Same thing here. If the area doubles, the EMF will double. This is true. Yes, the area will double. The EMF will double. This is true. So this will increase. So yeah, this is fine. Best answer here. Why did I draw a tick? Ignore that, that's an X. This is the answer, because this should have said halved. It didn't. So that's why B is the answer. Now, you need to know only a couple of things about generators. They're both generators. One is DC, one is AC. And I almost gave it away by moving the mouse. The only real difference you need to remember is here. There is one commutator ring, one split ring. Sometimes it's written as split ring or split commutator ring. It's got a little gap in the middle. This one has 2 rings, otherwise known as slip rings. So one ring is DC, 2 rings is AC. That's it. So looking at this one here, figure A is DC, figure B is AC. That's the only thing you really need to know. You don't need to know about the inner workings of it, so I can ignore that for now. So just remember that. For a graph, DC is one direction only. DC ends up being positive only. AC will be positive and negative because the current's changing direction, right? So in this case, this is direct current, and the next one must be alternating current. So that means the best answer, straight away I can see it, will be A. Very good. Right, what is this? The electric field along a closed path is related to the change of the magnetic flux by this equation. This tells us what? All right, so we have E. That's electric field, not B, magnetic field. It's E, electric field. E ds equals negative D flux B, magnetic flux, not E, not electric flux, magnetic flux over time. So I can see magnetic flux, electric field, I see magnetic flux EMF, I can see electric flux, magnetic field, and electric flux EMF. What the heck? Right, first things first, I can see that I'm discussing a field and a flux. There is nothing about an EMF over here, no voltage. That E is not EMF, the EMF is epsilon, which looks like that. It's a little bit different. That's E, that's epsilon. So this is E. So I know automatically B is definitely wrong, and I know that D is definitely wrong. What I'm going to do now is see which one corresponds to the letters given in this question. So you can clearly see that I have an electric field, and a magnetic flux, B, magnetic flux. This looks good. Let's check the next one. Let's check C just to be safe. Electric flux. That's my flux? No, that's wrong. That's B. This is wrong. It's not electric flux. Induces a magnetic field. That should have said B if it said magnetic field. If C was to be correct, it should have said B over here, and it should have said E over here. It does not, so this is definitely wrong. The best answer has to be A. The magnetic flux is linked with the electric field. So keep that in mind. Just check the letters and make sure it works. Very good. So this question here, this one is saying, what are the units for induction? So we need to figure out the unit for induction. How did these appear? We'll get rid of that. So we of course know it is Henry. Okay, that's the general unit that we're using, named after the scientist. And then we have these two over here. That's joules per amp squared, and this is Tesla meter squared per amp. So how are we going to figure that out? So that's got joules in there. So that's my energy formula. U equals a half Li squared. So let's see if this is correct. So what I'm going to do is rearrange for L. I'm going to take my L equals half, doesn't really have a unit, but I'll keep it there, a half over I squared. You can see that this is joules per ampere squared. The unit for energy is joules. The unit for current is amperes. Joules, I've ignored the half because it's a constant. It doesn't matter. I can ignore it altogether. It's not important. This is important. Joules per amp squared is good. So I like that one. Next, let's see if this is correct. So what I'm going to do is I'm going to, well, where am I going to do it? I'll change the color and use blue. And let's do it over here. This is talking about the other formula for inductance. So we've got the EMF equals, first of all, we have negative N flux over time. To find the inductance, we have to use the formula L equals, how did we do this again? Ah, yes, we did. We did the EMF is lit, because we were trying to figure out lit, aren't we? Li over T. So I'll rearrange this to get lit. I wrote that for a reason. I'll get to that in a second. So this one here is L equals, well, I'll multiply. So E multiply by T, and I'm going to divide for current over I. So now, this is my EMF. I know the EMF is negative N flux over time. I can actually substitute that into here. Negative is not really important because there's a negative there, so the negatives will end up cancelling. So let's see what happens when I substitute it in. E equals negative N. Well, the N is 1, so I can kind of ignore it. It's just a number, and well, I'll write it. N. Flux, if you remember, is BA cos theta, BA. So we're going to ignore the minus, we're going to ignore the N, we're going to ignore the cos, because that's not important into the actual unit. But I can write it. Cos theta, oh my god, I didn't really plan this out very well, did I? Multiply, so there is my EMF, I've written that here, I've divided that by time, and I have to include the time up here, obviously, and I have the current down here. You can see that straight away the time and the time will cancel, and to simplify a bit better, we have the N, which is 1, I have the B, I have the A, I have the I. Okay, what's this? B. B is Tesla. A is area, meter squared. The current is amps. Tesla, meter squared per amps. These are the variables with the units. That doesn't have a unit, that's just a number, and usually it's just 1 anyway. And the angle itself is an angle, and imagine we can just say it's going to be full. Cos of 0, it'll be nothing. It will not be nothing, it'll be full. Ignore it. This is the variables, and well, these are the variables. My English obviously sucks now. Too much physics going on. Tm squared over A. Tm squared over A. That's correct. I don't like the fact that I changed the color. Let's go back to red, the good teacher's color. All 3 are correct. Very nice. So energy can be stored in many ways. For an inductor, well, we've been talking about this for weeks and weeks now. Inductors is all about magnetic fields. How do I know that? Right there, B. B is the magnetic field. So that's the answer directly. O opposes the change in, so an inductor is supposed to oppose the change in current. It is an inductance, so that's the whole point, so it obviously can't be that. The resistance is the resistance, it's not changing. To be honest, if you do change the resistance, you can change the current, but the whole goal is to change the current. You could also say voltage, changing the voltage will change the current. So actually, if current was not an option, you could maybe select A, but the one we're looking for is current. It's the change in current over time. So that is my inductance, because it's part of the formula, right? There it is, the change in current over time. So there we go. Moving on to the next one here, which is the largest inductance. This is a solenoid, so we're going to think about the solenoid formula. We know the solenoid formula is the luna. L equals luna, the length. Inductance is capital L, length is small l. Mu, that's a constant, 4 pi times 10 to the minus 7, not important. N, number of turns per meter, squared. A, very good. This is the rule. You can see it's directly proportional to all of them. In fact, I can just multiply them together to get the answer. I don't need the mu. You could actually solve it individually, getting the answers, but it's going to take forever. I can ignore the mu, and I know this says here radius. I'm supposed to do pi r squared, but the numbers are so small, it'll be nice and easy just to multiply them. 1 times 5 is 5 times 100, that'll be like 500, yeah? It's not the real number, of course, that is wrong, but I'm going to just see which one will give me the biggest one out of these, and then that will clearly be the largest inductance. You can verify by doing the actual calculation and getting the full answer, but we don't have time. In a multiple choice in an exam, you need to be able to answer it quickly. 3 times 1 times 100 will be 300. 2 times 2 is 4, that's 400. 2 times 5 is 500. 500. So in this case, I can see that they're all the same. Have I messed up? 2 times 5 is 10. Oh my God, I am so bad. Maybe I'll edit this. I can't be bothered editing it. 2 times 5 is 10. 10 times 100 is 1,000. There we go. So we have 500, 300, 400, 1,000. D is the answer. That's going to be the biggest one. You can verify by doing the calculation. Which of the following statements regarding self-induction is correct? So it only occurs when there's a direct current flowing? No, because direct current flowing just simply means a steady current in one direction. I have to change the direction of the current. It only flows when alternating current is flowing through it. Yes, it needs alternating current. So this looks good, but let's see what else we have. Self-induction when either AC or DC is flowing. Well, we've already said DC is not good enough, so that's not going to happen. But let's look at D. This is the little tricky thing. Look at this. It says here, when either DC or AC, as long as the current is varying. Varying means changing. Like I said, more importantly, the current must be changing. So although this looks good, it's not only the reason. If I have DC and I have a switch and I turn it on or turn it off, that will be changing the current. Turning it on, the current begins to flow from 0. Turning it off, the current will drop to 0. That is a change. There will be a self-induction over there. So D is the best answer for self-induction. So there's something you need to know about self-induction and mutual induction, which I have covered in a previous video. You can check that out as well. Next, an inductor has this inductance. It generates this, and current should change at a rate of. Sorry, I'm going to have to erase this stuff, but if I erase it, then when you're reviewing, you won't see it. Forget it, I'll keep it here. You can see that. A rate of, remember, what did I say? If I do anything of a rate, that means I'm dividing by time. Look, dividing by time, that's seconds. So that means I need to figure out the formula. I have EMF, it's written already over here, negative Li over T. And what I'm trying to do is find the rate, current over time. Current over time is my rate. How do I rearrange the formula? You can see it's magnitude only, so I don't need the minus. E over L equals I over T. That's it. All I need to do is the E over L part. The E is the EMF. I will do, right over here, 2 divided by 4 milli times 10 to the minus 3. Milli is minus 3. If I was to put that into my calculator, I should hopefully get 500 amp per second. That it is. Very nice. Over here, we have the same idea. What is the magnitude of the voltage inductors at the time of that? So I did do some of the derivatives with you in previous lessons and videos, so we'll continue on with that, assuming you know how to take derivatives. You can see that I is given as a function of time. I is given as a function of time. You can also see that because it's I divided by t, I'm going to write over here, di by dt. That is a derivative. Dividing, derive, divide, derive. Will be the antiderivative if they were to be multiplied in the equation. But no, I am dividing the current with the time. I must take the derivative for that reason. Taking the derivative of this is actually really straightforward. That will become nothing. That just becomes 9. The t will disappear. That becomes 3 times 2. That becomes minus 6t. The 2 will disappear after that. I will now substitute that t into the formula. What I can do is now I can just figure this out by doing the EMF equals negative L, and my derivative that I've just found, I'll write it here, I over t. I don't know why I wrote it again. I just did, for fun. Okay, negative, what's this? 5.6 milli. 5.6 times 10 to the minus 3, multiply that by, and in my bracket, I'll have my function, and I'll just substitute the t into it. 9 minus 6 times 4. 6 times 4 is what? 6, 12, 18, 24. 9 minus 24. Very good. Solving that with the calculator, no idea why I used my brain, I've got my calculator here. Solving that in the calculator, I'll get 0.058. EMF equals 0.058 volts. So, 1, 2, 3. That is the same thing as me moving the decimal point to here, becoming 58, and I moved the decimal point 3 times, right? Times 10 to the minus 3, taking you back now all the way to grade 9, term 1, week 1. We did all this. Okay, very nice. Volts, that's millivolts. 58 millivolts, done. Now let's get on with the good stuff. Over here we have mutual induction. Mutual induction, so the rules are the same for Lenz's law. If I have a current flowing that way and it's getting stronger, it will be in the opposite direction. If it's flowing that way and getting weaker, it will be in the same direction. All right, so what's happening over here when the coil is opened? It's opened, meaning it's going to be getting weaker, right? The current will stop, slowly stop. It must be in the same direction. So you can see number 1 is in the same direction. A current is induced in coil 2 that flows in direction 1. I like it, so that is correct. That's it. What's this? How much energy is stored when 50 amps flows through a 20 Henry inductor? Nice and easy. U equals a half Li squared. U equals a half times 20 times 50 squared. So solving that answer, you should hopefully get, what will you get? You will get this number here, 25,000. There we go, we have the answer already. Over here, which current is changing more rapidly? So that's the I over T again, rapidly, the rate, how fast it's changing, I over T. I've rearranged it so many times, I'm just going to directly go to here, rearranging the rule. EMF over L. 2 divided by 2, that will be 1. 4 divided by 1, 4 divided by 1 is of course 4. So that means which one is changing faster? I2 is changing faster, not that one. I2 is changing faster, I2 right there. Over here we have the inductor. It has a time-dependent current flowing over it, short period of time, very nice. What is the magnitude of the EMF? EMF at time 0.3, which is here. Well, it's negative L I over T, right? L we have 75, negative, you can see the minus is not important. L, which is, what is L? I just said it, 75. 75 multiplied by I over T. So the time is 0.3. You will maybe look at this and you'll see, okay, well then that's my current at 0.7. You would be wrong. It's the change of current over the change of time, technically speaking. The current didn't start from 0. It's the slope of the graph. You can take the slope of the graph, or you can just realize that I started from 0.1 and I finished at 0.7. Final minus initial, right? So you can do that right now. I can do 0.7 minus 0.1 divided by the time, 0.3 minus 0. This is a slope. 0.3 minus 0, I don't need to write that part, but I've written it anyway. Putting this into your calculator, hopefully you will get the answer of 150 volts. Very good. All right, very nice. So next, how large of a current will flow through this to get energy? That's just same formula, but I can shift solve and get I, or rearrange the formula. I can write, I'm just going to put the number straight in right now, 393 equals a half, there's my half, L 1.2 times I squared. So let's solve it using shift solve. I will get 25.6 amps. Over here, now we're going to see what happens in this case when we're talking about the inductance being halved and the current being doubled. What will happen to my energy? So U equals a half Li squared. So there is a trick that I've given to show you how to just solve this pretty straightforward, easily. You're supposed to take a ratio, figure out the start and the final, and then arrange and whatever. I'll show you what to do. I will ignore any constants. If there is a half, it doesn't matter. It's not a variable. It is a constant, a half of everything. So that's a half, I can ignore it. If there was a pi in here, I will ignore it. If there was a mu, I will ignore it. If there was a k, I will ignore it. I don't care. I only care about the variables. So I'm going to ignore my half. I have my original, let's just say it was 1, and I'll times it by 1. And of course, I will just get, well, 1, right, originally. Now, look what happens when I change the variables it asked me to. So what am I going to change? What is the energy stored if the current is doubled? So the current is doubled, the inductance is a halved. L will become 0.5, a half, multiplied by 2 squared. Obviously 2 squared is 4, times by a half is 2 again. So I will have 2. It becomes double. If you really wanted to, because there's a couple of minutes left in this video before I have to cut it off, I will just show you. Originally, if you did keep it, so I'm going to change the color to blue, because if you're happy with what we've done, stop now. If you wanted to check the ratios out, you can check including the half. If you don't like the fact that we cancelled it, let's check. Originally, you will check 1 over 2, multiply that by L, which we will originally assign as 1. Squared, that will just give me, well, a half again, 0.5. So my answer here will be a half. Okay. If I now change my variable, I will do a half times that 0.5. I'll write it as a half again. Why not? Multiplied by, I doubled that, didn't I? So what does that give me? This will give me 2 squared is 4, half of 4 is 2, half of 2 is, well, basically 1, right? But that's not finished. It's a ratio. All I need to do now is divide. I will take 1 divided by a half. Directly, I get 2 again. See that? It's an extra step. I don't like doing extra steps. I'd rather get this done fast when I'm solving these questions. So I like to stick with this. And I will stop this video now because it's been going on long enough. Thank you.